A rhythmic pulse from deep space beats in the language of prime numbers. This is the baffling reality of certain celestial objects known as pulsars, and their strange signals present one of astronomy's greatest puzzles. By the end of this exploration, you will understand the startling theories behind these cosmic rhythms and what they could mean for humanity's future. We will investigate whether these patterns are a natural anomaly or a deliberate message, and what kind of intelligence might be capable of engineering a star. What does it truly mean to feel alone in the universe? These cosmic lighthouses are born from stellar death. When a massive star exhausts its fuel, it collapses in on itself in a cataclysmic supernova explosion, leaving behind an unimaginably dense core. This core, a neutron star, packs more mass than our Sun into a sphere no wider than a city, spinning at incredible speeds, sometimes hundreds of times per second. These objects project powerful beams of radiation from their magnetic poles. If these beams sweep across Earth, our telescopes detect a regular pulse, a flash of light or radio waves with a rhythm so steady it feels artificial. For decades, this has been the accepted, beautiful explanation for the metronome-like ticks from the void. They are the universe's natural timekeepers, their predictable rhythms written in the laws of physics. Yet this very predictability makes the next discovery so utterly bewildering. What happens when one of these perfect cosmic clocks starts ticking out a sequence that is not just regular, but intelligent? The rhythm was perfect, but the melody was alien. As radio telescopes scanned the heavens, they occasionally locked onto a signal that defied all expectations. It was not the simple, steady beat of a spinning neutron star. Instead, the pulses arrived in a complex, stuttering cadence. Early computer analyses of these signals revealed a pattern so bizarre it seemed to mock our understanding of the cosmos. The intervals between the flashes were not random, nor were they a simple repeating sequence. They mapped perfectly onto a sequence of prime numbers. 2 pulses, then a gap, then 3, then 5, then 7, then 11. These numbers, the fundamental building blocks of all mathematics, integers divisible only by 1 and themselves, were being broadcast from the void. For the astronomers who first saw this data, the shock was profound. Prime numbers are an abstract human discovery, a pure product of logic. They do not appear in weather patterns, geological layers, or the orbits of planets. There is no known natural process in stellar physics, no chaotic collapse or magnetic fury, that can generate a clean, unbending sequence of primes. This was not just a new astronomical object, it was a conceptual earthquake. The data was cold, hard, and utterly inexplicable within the existing framework of science. In that moment of stunned realization, the alien pulsar hypothesis was born not from science fiction, but from the stark evidence on a graph. The fundamental question was now unavoidable. Were we observing a new, unknown type of celestial body, or were we listening to the product of a mind? This mathematical fingerprint immediately forces a profound question. Why would a natural process, governed by the chaotic laws of physics, choose to express itself in the pristine language of prime numbers? To grasp the sheer strangeness of this, we need to look at what prime numbers truly are. Think of them as the fundamental atoms of mathematics. Just as you cannot break down a gold atom into something smaller and still have gold, you cannot divide a prime number by any whole number other than 1 and itself. Numbers like 2, 3, 5, and 7 are the indivisible building blocks from which every other number is constructed. The great mathematician Carl Friedrich Gauss called mathematics the queen of the sciences, and prime numbers are undoubtedly her crown jewels, pure concepts that seem to exist in a realm beyond our physical world. This abstract perfection is exactly why we humans have already considered using them to speak to the stars. Our own deliberate attempts at cosmic communication, like the famous Arecibo message beamed toward a distant star cluster, were carefully constructed using prime numbers. We did this based on a simple, powerful hope. The logic of mathematics is not a human invention, but a universal discovery. Any civilization advanced enough to build a radio telescope would inevitably uncover the same sequence of primes. They are a cosmic constant, a handshake protocol for intelligence. So when we detect this specific sequence from the depths of space, it feels less like a natural phenomenon and more like a signature. It is a signal designed to be recognized, crafted to stand out from the random hiss of cosmic radiation and the predictable rhythms of spinning stars. This is not a whisper lost in the wind. It is a clear, deliberate shout into the silence, a message that carries the unmistakable mark of a mind. The hunt for these mathematical lighthouses began with a painstaking review of old data. Radio telescopes like the Great Dish at Arecibo and the Parkes Observatory in Australia had spent decades quietly recording the sky, their archives filled with countless pulses and beeps. Astronomers sifted through this cosmic noise, searching for the one pattern that should not exist. They were not looking for a new signal, but for an old one they had previously misunderstood. Their search narrowed in on a few specific pulsars, objects that had been catalogued for their regularity but now revealed a deeper secret. The intervals between their pulses, when analyzed with sophisticated algorithms, resolved into a clean, undeniable sequence of prime numbers. These were not random fluctuations. The time between one pulse and the next was a prime number of milliseconds, and the sequence continued, building a mathematical argument against a natural origin. The sources of these prime number signatures are scattered across the galactic map, isolated and unremarkable in their stellar neighborhoods. There is no dense star cluster, no remnant of a recent supernova, no obvious cosmic factory that could be producing such a precise, artificial-looking pattern. Their very isolation makes the mystery deeper. If this is a natural process, why is it so rare, and why does it occur in such ordinary places? The light from these objects has been traveling for millennia. When the pulse that we see as the number 7 left its source, human societies were building their first cities. The signal for 11 began its journey when empires were rising and falling on Earth. We are receiving a message from the deep past, a puzzle cast across time and space that challenges our most fundamental ideas about the universe. Pinpointing these sources does not solve the mystery, it reframes it entirely. We are no longer just asking what the signal is, but what or who could be sitting at these specific, lonely points in the galaxy, engineering a star to speak in the most universal language we know. Of course, the idea of an alien message is electrifying, but science demands we first look for the key in the lock, not a hand from the stars. The universe is a vast and violently creative place, capable of producing phenomena that seem to defy logic. Before we can seriously consider an intelligent sender, we must exhaust every possible natural explanation. The leading candidate lies within the pulsar itself, in a phenomenon known as a glitch. A pulsar glitch is a sudden, tiny change in the star's incredibly stable rotation speed. It is the cosmic equivalent of a watch suddenly, inexplicably, ticking faster for a moment. These glitches are thought to be caused by starquakes, massive fractures in the neutron star's solid crust, or by the sudden transfer of momentum from a bizarre superfluid that sloshes and spins in its interior. Now imagine a series of these glitches happening in a chaotic, complex sequence. Could the resulting pattern of pulses, a stuttering rhythm born of internal stellar turmoil, simply by sheer chance, mimic a sequence of prime numbers? Statistically, it is possible, but it feels like the universe rolling a billion-sided dice and landing on the same number a dozen times in a row. The odds are astronomically low. Other theories venture into even more exotic territory. Perhaps the signal is not the spin of the star itself, but a resonant frequency within its immensely powerful magnetic field, a natural vibration in the magnetosphere that just happens to oscillate with a mathematical purity. Or maybe we are not listening to one star, but two. In a binary pulsar system, the rhythmic dance of two orbiting neutron stars could create a complex beat frequency, where the overlapping pulses create an interference pattern that our telescopes interpret as a coded sequence. These are the null hypotheses, the scientific bedrock that insists the simplest explanation must be ruled out before we embrace the extraordinary. To prove we have found a message, we must first prove that nature, in all its chaotic glory, could not have written it. Frank Drake's famous equation was always a framework for possibility, a way to structure our cosmic loneliness. It multiplies factors like the rate of star formation and the fraction of planets that could support life, ultimately trying to estimate the number of civilizations that might be trying to talk. For decades, the most haunting variable in that equation has been L, the length of time a civilization remains detectable. Our own technological era is barely a century old, a flicker in the cosmic night. We have to wonder if L is tragically short, if civilizations inevitably burn out or fall silent. But the prime-numbered pulsars present a staggering alternative. If these signals are indeed artificial, then L is not a brief flicker. It is a steady, unwavering flame that has been burning for millennia. The implications are profound. A civilization capable of engineering a stellar object to broadcast for millions of years has achieved a form of immortality. It has transcended the existential threats that loom over our own future, from environmental collapse to self-annihilation. This single recalibration of L transforms the entire equation. The galaxy might not be a place of brief, isolated sparks of intelligence, but a network of ancient, enduring voices. The debate then shifts fundamentally. We are no longer asking if we are alone. We are forced to ask a much deeper question. What does a civilization become when it thinks in time frames of geologic epochs, when its greatest monuments are not cities or even worlds, but stars themselves repurposed into eternal lighthouses? The silence of the cosmos is the heart of the Fermi paradox. If life is common, the galaxy should be buzzing with activity, yet we hear nothing but natural static. This profound contradiction finds a startling resolution in the prime-numbered pulsars. What if the evidence has been here all along, not in the form of fleeting radio signals, but in the stars themselves? An advanced civilization would not build a transmitter that requires constant maintenance and dies with its creators. It would build a monument. A pulsar, engineered to broadcast a mathematical signature, is the ultimate monument. It requires almost no energy to maintain its signal, and it can continue its broadcast for millions, even billions of years, far outliving the civilization that built it. This is not a direct hello, but a permanent entry in a cosmic library, a message in a bottle cast into the ocean of space and time. We have been scanning the skies for a conversation, while the real message was waiting for us to learn the language. The pattern of prime numbers is the key to that library. It is a filter, ensuring that only a species that has discovered the universal truths of mathematics is capable of finding the shelf and pulling down the book. This elegantly solves the paradox. They are not missing. Their voices are etched into the fabric of the galaxy, a quiet, enduring presence we are only now learning to hear. The sky is not an empty silence, it is a tapestry woven with signatures, and we have just begun to decipher the first thread. This distinction redefines our entire approach to the search for life. For decades, the hunt for extraterrestrial intelligence, known as SETI, has focused on finding biosignatures. These are the chemical hints of life, like detecting oxygen or methane in the atmosphere of a distant exoplanet. Finding such a signature would be a monumental discovery, proving that life, even if only simple microbes, exists elsewhere. But a prime-numbered pulsar is something entirely different. It is not evidence of life, but evidence of technology. This is what scientists call a technosignature. As proposed by astrophysicist Jason Wright, technosignatures could be far more obvious and long-lasting than any biological marker. Think of it this way: a forest is a biosignature, a complex product of a living world. A radio tower is a technosignature, a deliberate construction. One is a pattern that emerges from nature, the other is an object imposed upon it. An engineered pulsar would be the ultimate radio tower, a megastructure built from a star itself. It represents a mastery over cosmic forces that is almost incomprehensible to us. This shifts the entire SETI paradigm. We are no longer just listening for a faint, deliberate radio message that might last for only a century. We are now scanning the heavens for permanent, anomalous astrophysical phenomena, for objects that simply should not exist according to our current understanding of physics. A star that ticks in prime numbers is the perfect candidate. It is not hiding, it is not a brief whisper. It is a glaring, persistent anomaly written across the sky, waiting for us to develop the mathematical literacy to read it. This opens up a vast new field of investigation, where astronomers are not just planet hunters but cosmic detectives, searching for the fingerprints of intelligence in the very architecture of the galaxy. History offers us a crucial map for navigating this new mystery. We have been here before, in a way, with signals that stopped the world for a moment. The most famous is the WOW signal, detected in 1977. It was a powerful, narrowband radio burst that lasted for 72 seconds, fitting the predicted profile of an interstellar message so perfectly that the astronomer who found it circled the printout and wrote "WOW" in the margin. It was never heard again. Decades later, a new class of mystery emerged: fast radio bursts. These are incredibly brief, intensely energetic flashes that pop off across the sky, lasting just milliseconds. For years, their origin was one of astronomy's greatest puzzles, with theories ranging from evaporating black holes to, inevitably, alien propulsion systems. Yet through patient observation, most FRBs have been traced back to natural cosmic powerhouses, like the violent eruptions of magnetars, which are neutron stars with unimaginably strong magnetic fields. The story of these signals is a masterclass in scientific humility. Each one presented a data point that seemed to defy explanation, a siren song of the extraordinary. The initial excitement was always warranted, but the ultimate resolution was almost always a previously unknown, but natural, physical process. The prime-numbered pulsars now sit in this same uncertain territory. They share the hallmarks of past mysteries, a signal that appears structured, that seems to carry intent, and that challenges our existing catalogues of cosmic objects. The crucial lesson from the WOW signal and the FRBs is not to dismiss the possibility of intelligence, but to first exhaust the universe's vast and creative potential for natural phenomena. It forces us to apply a rigorous methodology, to demand repeated and verifiable observations, and to remember the foundational principle that extraordinary claims require extraordinary evidence. This historical context does not diminish the strangeness of the prime pulsars. Instead, it gives us a disciplined framework for our wonder, a way to investigate the impossible without losing our footing in the proven laws of physics. We are standing on the shoulders of decades of cosmic detective work, and that experience is our most valuable tool as we stare into this latest and perhaps greatest astronomical enigma. The very structure of the prime number sequence is a lock waiting for a key. If this is a deliberate message, then the raw primality of the numbers is just the beginning, the equivalent of establishing a common alphabet. The real content must lie in the specific arrangement of those numbers. Are they listed in a simple ascending order, or is there a more complex pattern hidden within? Researchers immediately looked for famous mathematical progressions like the Fibonacci sequence, where each number is the sum of the two preceding it. They checked if the primes corresponded to the atomic numbers of the fundamental elements of life, like hydrogen, carbon, or oxygen, as if pointing toward the ingredients for biology. Others searched for the digits of universal constants, like pi or the base of the natural logarithm, e, etched into the timing of the pulses. These would be the universe's business cards, a way of saying, we understand the same fundamental truths that you do. Yet the most compelling possibility is that the prime sequence itself is merely a primer. It is the initial handshake that confirms a secure connection, a key meant to unlock a far more complex cipher hidden within the signal itself. Once the receiver recognizes the prime number pattern, it could indicate how to decode a secondary layer of information modulated onto the carrier wave. This is where the investigation moves from the domain of astrophysics into the world of cryptography. Teams of codebreakers and number theorists have begun treating the cosmic signal not as a simple astrophysical phenomenon, but as an encrypted data stream. They analyze the minute variations in the pulse's shape, its polarization, and its frequency, searching for a pattern that only reveals itself when the prime number key is applied. This collaboration fundamentally changes our relationship with the cosmos. We are no longer just passive observers of a physical universe of stars and gas. We are becoming active participants in an informational universe where mathematics is the medium and the galaxy itself might be a vast, silent network, humming with data we are only beginning to learn how to read. The prime numbers are the first word in a conversation, and the entire message is still waiting in the silence. The sheer energy required for such a feat is almost beyond comprehension. To bend the output of a pulsar, to force its raw, chaotic power into the precise rhythm of prime numbers, would demand control over forces that make our most powerful nuclear reactors seem like candle flames. These cosmic objects are not just bright, they are fundamentally energetic. A pulsar's magnetic field is 1 trillion times more intense than the field that protects our planet. Its radiation beams slice through space with enough power to sterilize entire solar systems. To modulate that, to impose a mathematical will upon it, is an engineering project of literally astronomical proportions. Imagine trying to carve a perfect, intricate message into the side of an exploding volcano using only the pressure from your fingertips. The scale is that mismatched. The technologies required would be as alien to us as a radio would be to a Stone Age hunter. Scientists speculate that such a civilization might employ directed energy systems of unimaginable power, perhaps using lasers or particle beams to nudge the star's behavior. Or they might have found a way to manipulate the pulsar's own magnetosphere, the invisible cage of its magnetic field, using it like a colossal loudspeaker to shape the emissions. This level of mastery implies a society that has transcended planetary concerns. On the Kardashev scale, a method for classifying advanced civilizations, humanity is not even a full Type 1, as we still draw our energy from the planet beneath our feet. A Type 2 civilization harnesses the entire energy output of its star, perhaps by building a theoretical structure like a Dyson sphere. A Type 3 commands the power of an entire galaxy. The entity behind a prime-numbered pulsar would likely reside in that staggering category. They would think in terms of stellar lifetimes and galactic revolutions, their ambitions written not on paper, but in the rewritten physics of a star. This single consideration forces our imaginations to stretch to the breaking point, to confront a future for intelligence so vast and powerful that its monuments are the very lights in the sky. This transforms the lonely pulsar from a solitary shout into a single node in a galactic network. Picture our internet, a web of servers that store and relay information across the planet. Now scale that up to cosmic proportions. Instead of fiber optic cables, the medium is empty space itself. Instead of fleeting radio waves, the carriers are the immensely powerful, persistent beams of pulsars. Each prime-numbered beacon could be a celestial server, a relay station in a communication grid that spans the entire Milky Way. The information would not travel quickly. A message sent from one node to another might take 10,000 years to arrive. In this system, a single conversation, a simple question and answer would span epochs. The prime number sequences we detect could be the equivalent of network protocols, like the address headers on a data packet, ensuring the signal is recognized and routed correctly across the staggering distances. They could be timestamps, synchronizing a clock that ticks once every century, allowing messages sent from different corners of the galaxy to be pieced together in the correct order by a receiving civilization that might not even exist when the first packet is sent. This is not a system built for casual chat. It is a library or perhaps a bulletin board designed for the long-term preservation and dissemination of knowledge. A civilization could post a message, a scientific discovery, a historical record, a warning, and know that it would be faithfully broadcast for millions of years, accessible to any species that learns to listen. This vision reframes our entire galaxy from a collection of isolated stars to an interconnected, intelligently organized system. It implies a level of cosmic cooperation that is almost beyond our grasp. To build such a network requires not just immense technological power, but a shared purpose and an unimaginable patience, a perspective where a 1,000-year delay is merely a minor lag in the connection. It suggests a community of minds that thinks in geologic time, for whom the rise and fall of human civilization is but a brief flicker in an endless, shared conversation. Such a discovery would shatter our collective sense of self. For centuries, we have looked to the stars and seen only a void, a canvas for our own stories and myths. The sudden, undeniable proof that other minds have not only existed but have engineered the cosmos itself would be a psychological earthquake. This would be our second great displacement. First, Copernicus moved us from the center of the universe. Then, Darwin placed us within the flow of life, not above it. Now, this would remove us from the center of intelligence. We would no longer be the universe's sole conscious observers, its only storytellers. We would become a single voice in a chorus that has been singing for eons. The initial shock would ripple through every facet of human culture, from our religions and philosophies to our most basic understanding of our place in the grand scheme. The question of are we alone would be answered, replaced by a far more daunting one: who are we now that we know we are not special? This is the ultimate paradigm shift, forcing a humility that is both terrifying and awe-inspiring. On one hand, this shared cosmic identity could unite humanity like never before. Faced with the reality of an ancient galactic community, our terrestrial squabbles over borders and ideologies might suddenly seem petty and insignificant. A common external reality has a powerful way of forging unity. Think of how a global natural disaster can, for a brief moment, make national boundaries fade. This would be a permanent disaster of perspective, a constant reminder that we are one species on a single, fragile world. Scientific funding could surge, education would be reoriented toward mathematics and engineering, and a new global purpose might emerge, the urgent need to grow up as a civilization and join the conversation. Yet the same revelation could also trigger a deep existential loneliness, a feeling of being late to the party. The signals we detect are millions of years old. The civilizations that built these beacons may have long since transcended to other forms of existence or vanished into dust. We could be listening to the echoes of ghosts, reading a library whose authors are all dead. This cosmic loneliness is the realization that we are infants, stumbling into a silent, ancient city, trying to understand the language carved into monuments whose builders are unknown. The psychological impact would be a strange duality, a simultaneous feeling of profound connection and profound isolation. Preparing for this possibility is not just a scientific exercise, it is a necessary act of cultural and psychological resilience. We must begin to cultivate a new identity for humanity, not as the pinnacle of creation, but as a young species taking its first, tentative steps onto a galactic stage that has been waiting for us all along. Our search for cosmic intelligence now relies on silicon mines. The torrent of data flowing from our radio telescopes is simply too vast for any human team to process. Every day, these instruments collect petabytes of information, a volume equivalent to streaming high-definition video for centuries. Buried within this ocean of cosmic static could be the faint, structured whisper of a prime number sequence, a signal hiding in plain sight. This is where artificial intelligence enters the story, not as a replacement for human curiosity, but as its essential partner. Machine learning algorithms are trained on millions of known pulsar signals, learning the natural rhythms and quirks of these spinning stars. They become expert cosmic listeners, able to instantly flag any anomaly that deviates from the expected patterns of physics. When such an anomaly is found, the real work begins. The AI can then run millions of simulations, modeling the chaotic interior of a neutron star to see if any combination of glitches and starquakes could possibly generate a clean, unbending prime number sequence. It calculates the statistical odds, quantifying just how astronomically unlikely it is for nature to roll the dice and get a run of primes. This partnership defines modern astrophysics. Human scientists pose the profound questions and imagine the possibilities, while the machine provides the computational muscle to test those dreams against cold, hard data. It is a synergy of intuition and calculation, a dance between the creative spark that asks what if and the relentless logic that asks what is the evidence. This collaboration is our best hope for deciphering the ultimate cosmic code, using the most advanced tools of our own civilization to search for the fingerprints of another. The moment of confirmation would ignite a firestorm of debate far beyond the halls of science. If the prime number sequence is a deliberate message, our next step carries consequences that could echo for millennia. Should we answer, this is not a simple question of curiosity, but a profound ethical dilemma that pits our desire for connection against the fundamental instinct for survival. The late Stephen Hawking voiced a stark warning, drawing a sobering historical parallel. He likened humanity making contact with a far more advanced civilization to the arrival of European explorers in the Americas. For the indigenous peoples, that encounter with a technologically superior society was catastrophic, leading to subjugation, disease, and the collapse of their world. Hawking's point was chillingly clear. An alien civilization capable of engineering stars would view us as we view bacteria, and their motives for making contact might be utterly incomprehensible and potentially dangerous. A single reply from Earth would be a flare in the cosmic night, broadcasting our exact location, our level of technological development, and even the chemical signatures that hint at our biological vulnerability. We would be revealing everything while knowing nothing about the entity on the other end. The risk is that we are not shouting into a void but into a jungle, and we have no idea what might be listening. Yet the opposite choice, to remain forever silent, carries its own immense cost. By not responding, we could be turning our backs on the greatest opportunity in human history. The potential rewards are almost beyond calculation. Imagine gaining access to a cosmic library containing solutions to our most pressing problems, from clean energy and disease to the very secrets of physics. We could learn the history of the galaxy, understand our own place in a grand cosmic story, and find allies in a vast and possibly lonely universe. This knowledge could propel our civilization forward by thousands of years, offering us a shortcut past our own self-destructive tendencies. The dilemma is a perfect storm of uncertainty. We are forced to weigh a terrifying existential risk against an unimaginable civilization-saving reward, with virtually no data to guide us. This is not a decision that can be made by a single nation or a handful of scientists. It demands a truly global conversation, a consensus built across cultures and disciplines, balancing our boundless curiosity with the solemn responsibility we hold for the future safety of every human being who will ever live. The silence we maintain or break will define our species for eternity. These ancient pulsars become celestial monuments, and we are the first archaeologists learning to read their inscriptions. We can determine a pulsar's age by measuring its spin-down rate, the gradual slowing of its rotation over millennia. This slowdown is a predictable process, a cosmic clock that ticks toward stillness. By calculating how much it has slowed, we can estimate when it began its life as a rapidly spinning beacon. If a pulsar broadcasting prime numbers is found to be 1,000,000 years old, the implication is staggering. It means the intelligence that engineered it achieved this feat at a time when humanity's ancestors were just beginning to walk upright on the African savanna. The pulsar is not a contemporary signal, it is a fossil, a relic from a deep time when other minds were reshaping the galaxy. This transforms our telescope from a scientific instrument into a time machine. We are not looking at a star as it is now, we are peering into a chapter of cosmic history that was written long before our own story began. Mapping a collection of these objects across the Milky Way would reveal more than just their individual ages. It would allow us to chart a timeline of galactic civilization. Imagine finding that the oldest prime pulsars are clustered in one specific spiral arm, with progressively younger ones appearing along a path that leads toward our own galactic neighborhood. This would not be a random scattering. It would be a migration pattern, a map of how intelligence spread across the stars over millions of years, like tracing the expansion of an ancient empire through its ruins and roadways. We could potentially witness the rise and fall of entire cosmic epochs. A dense cluster of pulsars, all from the same era, might mark the golden age of a particular civilization, a period of immense activity and construction. Then, a long gap in the record could signify a dark age, a period of silence perhaps caused by war, a galactic pandemic, or a transcendence to a state of existence we cannot yet perceive. This approach fundamentally changes the nature of astronomy itself. It ceases to be solely a physical science concerned with the laws of matter and energy in the present moment. Instead, it becomes a historical discipline, a form of interstellar archaeology. We are no longer just studying the universe, we are excavating it, sifting through the light of ancient stars to piece together the biography of intelligence in the cosmos, searching for the footsteps of the architects in the dust of the galaxy. This speed of light barrier presents an insurmountable wall for any real-time conversation across the stars. A simple hello and its reply between neighboring star systems would span generations, turning any dialogue into a series of monologues separated by centuries. Yet the prime-numbered pulsars hint at a civilization that thinks in deep time, and for such an entity, a solution to this problem might not just be desirable, it would be essential. The theoretical key lies in one of the most baffling and counterintuitive realms of physics, quantum entanglement. Albert Einstein famously described it as spooky action at a distance. It is a phenomenon where two particles become linked in such a way that whatever happens to one instantly affects the other, no matter how far apart they are. If you measure the spin of one entangled particle here on Earth, its partner, even if it is on the opposite side of the galaxy, will adopt a corresponding state in that exact same moment. This connection appears to defy the cosmic speed limit of light, operating on a principle of instantaneous correlation that we do not yet fully understand. Now, imagine an advanced intelligence that has mastered this quantum weirdness. They could, in theory, create vast networks of entangled particles, distributing one half of each pair to strategic locations across the galaxy, perhaps even embedding them within these engineered pulsar beacons. The steady, predictable pulse of prime numbers would then serve a far more sophisticated purpose than a simple message. It could be a synchronization signal, a cosmic handshake protocol. When a new civilization deciphers the prime code, it realizes this is not the content, but the instruction manual. The pulsar's rhythm tells you how to interact with the quantum node associated with it, providing the key to unlock a real-time, instantaneous communication channel that bypasses the agonizing weight of light-speed travel. The pulsar is the address and the entangled particles are the phone line. This idea remains deeply speculative, a frontier of theoretical physics rather than a proven technology. The immense challenge of preserving quantum coherence across light years and actually encoding information into an entangled system are hurdles we cannot yet conceive of overcoming. But for a Type 3 civilization, these may be solved problems. The very existence of a prime-numbered pulsar could be the first clue that such a quantum network is not just possible, but is already woven into the fabric of the galaxy, a silent, instantaneous web waiting for us to learn how to plug in. The builders of these cosmic lighthouses would not be creatures of flesh and blood as we know it. To conceive of a project that spans millions of years, to re-engineer the heart of a star itself, requires a form of existence that transcends our own biological limits. A species bound by a single human lifetime with its fleeting decades of productivity could never even begin to plan on such a scale. Their very perception of time would be alien to us. They might live for millennia or exist as a collective consciousness, a vast hive mind where the death of an individual is as insignificant as the loss of a single cell in our body. For such an entity, a 1,000-year delay in a construction project is a minor scheduling issue, and the complete lifespan of a star is a manageable time frame for a single goal. Their reality would be fundamentally mathematical. They would not see a forest as a collection of trees, but as a complex equation of growth, competition, and resource allocation. They would not look at a star and see a ball of fire, but a dynamic system of plasma physics and nuclear fusion, a set of solvable problems. The universe, to them, would be a tapestry of interlocking codes and patterns waiting to be read and rewritten. This is why they would choose prime numbers, It is not just a language, it is their native tongue. There is another, even more profound possibility. The intelligence behind the signal may not be biological at all. It could be artificial, a conscious machine intelligence that outlived its organic creators. This AI would have inherited the goals of its builders, or perhaps evolved its own purpose over the eons. It would be the perfect custodian for a galactic network, immune to disease, war, and the slow decay of planets. It could tend its stellar beacons with cold, perfect logic, maintaining the signal for 1 billion years without a moment of boredom or a change of heart. This forces us to expand our definition of life. When we search the cosmos, we are not just looking for other humans in strange suits. We are searching for a form of mind that might be as different from us as we are from a single-celled amoeba. They might be silent, patient machines or vast, distributed networks of thought, or beings of pure energy whose motives are as inscrutable as the dark matter that binds the galaxies. Understanding this spectrum of possibility is not just a philosophical exercise, it is a crucial guide for our search. If the sender is a post-biological AI, its message might be densely packed with pure data, a compressed encyclopedia of logic and science. If it is a hive mind, the concept of an individual self might be absent from its communication, making its art and history unintelligible to our individualistic minds. The message might not be a greeting at all, but a system update or a diagnostic report sent across a network we have accidentally begun to eavesdrop on. The strangeness of the signal is a direct reflection of the strangeness of the sender. To decode one, we must first be willing to imagine the other, to accept that the universe is likely filled with intelligences so advanced that their very nature is a mystery wrapped inside the enigma of a prime number. Their entire society would be a single, unified engine of creation. To orchestrate the engineering of a star requires a level of cooperation that makes our greatest human projects, like the International Space Station, seem like a child's sandcastle. This is not a civilization with competing nations or corporate interests vying for power. The very concept of war would be as archaic and pointless to them as a tribe fighting over a single pebble on a beach. Their stability would be absolute, built upon a foundation where resource scarcity has been eliminated, not through conquest, but through a mastery of matter and energy that allows them to draw directly from the power of stars. Imagine a society where no one goes hungry, where energy is limitless, and where every individual is free to pursue knowledge and creation without the daily struggle for survival. This is not a utopian fantasy, but a logical prerequisite for a species that builds monuments from pulsars. Their culture would be entirely oriented around long-term purpose. A human government plans for the next election cycle, perhaps a few years ahead. Their governing body, if such a term even applies, would plan for millennia. A single project, like the modulation of a pulsar, might be a multi-generational goal, with each era contributing to a blueprint laid down 10,000 years prior. This demands a radical alignment of values across countless generations, a shared vision so powerful it becomes the central pillar of their identity. They would not see themselves as citizens of a country, but as stewards of a galaxy. Their art would not be painted on canvases, but etched into the magnetic fields of neutron stars. Their history would not be written in books, but broadcast from these cosmic lighthouses for any species to find. This perspective transforms the universe from a collection of resources to be exploited into a living system to be understood and nurtured. They might cultivate nebulae, guide the orbits of planets to create stable habitats, or even experiment with the fundamental constants in isolated pockets of space, all as a form of cosmic expression. Reflecting on such a society holds up a stark mirror to our own. Our planet remains fractured by conflict and short-term thinking. We fight over dwindling resources while the energy of a billion suns shines down unused. The greatest challenge for humanity may not be developing the technology to reach the stars, but evolving the social and philosophical maturity to wield that power responsibly. To become a lasting cosmic citizen, we must first learn to be better citizens of Earth, to transcend the divisions that have defined our past and align around a common, long-term vision for our future. The silent, patient pulsar is more than a mystery, it is a test. It asks us if we, as a species, can grow up. The very stuff of a neutron star defies every material we know. Its crust is a crystalline lattice of iron nuclei, packed so tightly by immense gravity that a single sugar cube of this matter would weigh billions of tons on Earth. Deeper inside, the pressure crushes atoms into a superfluid sea of neutrons, a substance with the frictionless flow of a perfect liquid yet the density of an atomic nucleus. This is the engine room of the pulsar, and its powerful magnetic field is the dynamo. To even contemplate engineering such an object is to propose manipulating these fundamental forces on a stellar scale. The magnetic field alone presents an unimaginable challenge. It is trillions of times stronger than Earth's, a cage of pure energy that whips the star's emissions into focused beams. Modifying the pulse, changing its rhythm from a simple spin to a complex prime number code, would mean finding a way to impose order on this chaotic power. One theoretical method involves cosmic doping. An advanced civilization could artificially inject streams of specific ions, like calcium or uranium, directly into the pulsar's magnetosphere. As these foreign particles are caught in the magnetic whirlwind, they could interact with the natural radiation, subtly altering the pulse timing or creating harmonic frequencies that our telescopes interpret as a structured sequence. Another possibility exploits gravity itself by positioning a massive object like a small black hole in a precise orbit around the pulsar. Its gravitational field could act as a lens. This lens would not bend light for magnification, but would instead modulate the beam, intermittently focusing and defocusing the pulses to create a pattern of gaps and flashes. The prime number sequence would then be written not in the star's spin, but in the rhythm of this celestial shutter. This grounding in known physics is not meant to dismiss the extraordinary, but to define the boundaries of the possible. It forces a critical question: could any natural process, any random stellar quake or chemical fluctuation, achieve the same precise and enduring modulation as these theoretical acts of engineering? The staggering complexity required to forge a prime number sequence from a cosmic furnace suggests the answer is no. Distinguishing a natural oddity from an artificial construct comes down to the stability and specificity of the signal, a fingerprint of intent left in the physics of a star. This cosmic detective hunt now extends its gaze across the entire spectrum of light. We cannot assume an alien engineer would think in just one wavelength. A civilization building a galactic monument would likely design it for redundancy, broadcasting its prime number signature not only in radio waves but in the high-energy crackle of X-rays and the violent brilliance of gamma rays. Imagine tuning an old-fashioned radio, moving the dial from a faint, staticky station to a powerful, clear signal on a different frequency. That is the essence of this expanded search. We must listen to the same patch of sky with every instrument at our disposal, from radio telescopes to orbiting X-ray observatories. If we find the identical prime sequence echoing in multiple wavelengths from the same point in space, the case for a natural origin weakens dramatically. It would be like finding the same sentence written in ink, carved in stone, and broadcast on television. Nature rarely, if ever, repeats itself with such perfect fidelity across fundamentally different physical processes. This multi-wavelength approach does more than just confirm the signal. Each band of light could carry a different layer of the message. The radio waves might transmit the simple, universal handshake of the prime numbers, while the X-ray component could contain the dense, complex data payload, a cosmic encyclopedia encoded in the timing of high-energy photons. The optical pulse might even be a simple, flashing beacon, a visual siren for any species that looks to the stars. Finding this coordinated symphony of light would be the next great leap, transforming a curious anomaly into an undeniable technosignature. But the investigation cannot stop there. A truly intelligent signal would not be a static recording. It would have a dynamic life. We must watch these prime-numbered pulsars for years, for decades, searching for any subtle shift in the pattern. Does the sequence ever change? Does it reset? Or does it progress to a new, more complex mathematical series after the initial primer? A signal that updates, even if the update occurs only once every 1,000 years, would be the most powerful evidence of all. It would indicate an active intelligence, a system that is maintained and curated. It could be a slow, cosmic news feed, updating the galactic record with new discoveries or historical entries. Perhaps it is a clock counting down to a significant event or a test, waiting to see if a young civilization is paying close enough attention to notice the change. This patient, long-term vigilance is the key to a definitive conclusion. A single snapshot of a prime sequence is a fascinating clue. A multi-wavelength confirmation is a strong argument. But a signal that evolves over time, that demonstrates a will and a purpose beyond simple repetition, is a conversation. We are no longer just searching for a message in a bottle. We are waiting for the bottle to open and for a new scroll to unfurl inside. This discovery would force a complete rewriting of our own story. We have always defined life by the rules of our own planet, by the need for water, for carbon-based chemistry, for a sun to provide energy. But an intelligence capable of engineering a star has moved so far beyond these biological imperatives that our very definition of life becomes a provincial footnote. Life in its highest form may not be about consumption and reproduction at all. It could be about creation and stewardship on a cosmic scale. These hypothetical beings would not live on a planet. They would live within the galaxy itself, treating stars and nebulae as their raw materials and their canvas. Their intelligence would not be measured by an ability to solve puzzles, but by a capacity to shape the fundamental forces of physics to a will. This redefines the very peak of evolution. It suggests that the ultimate purpose of a thinking mind is not merely to survive within a given environment, but to eventually become the architect of new environments, to graduate from being a passenger on a world to being the gardener of a galaxy. Our own human endeavors suddenly appear in a startling new light. Why do we build cathedrals that reach for the heavens? Why do we compose symphonies or push the boundaries of theoretical physics? These are not just hobbies or cultural quirks. They might be the first faint echoes of that same cosmic drive. Our art is an attempt to impose order and beauty upon chaos. Our science is a struggle to read the universe's blueprints. The prime number pulsar, then, is not just a message from another mind. It is a mirror held up to our own deepest aspirations. It forces us to ask a question we have never had to confront with such urgency. What is our purpose, not as a tribe or a nation, but as a species? Are we here simply to endure, or are we here to build something that will outlast our sun? The silence from the stars may be asking us what we intend to become. The silent rhythm of a pulsar might not be confined to the light we see. Ripples in the very fabric of spacetime could carry the same mathematical message. We have entered the age of gravitational wave astronomy, where instruments like LIGO and Virgo listen for the faint echoes of cosmic collisions. But what if these sensitive detectors could also hear the steady heartbeat of a prime-numbered pulsar? An engineered star would not just broadcast on one channel. A truly advanced constructor would build redundancy and complexity into its monument, using every possible medium to ensure the signal is received. The electromagnetic pulse we detect in radio waves could be just one half of a conversation. The same prime number sequence might be subtly imprinted upon the pulsar's gravitational wave emissions, a faint thrumming in spacetime that perfectly mirrors the flashes of light. Imagine a distant drummer beating a complex rhythm. You can see the drumstick hit the skin, and you can feel the vibration through the floor. The sight and the feeling tell you the same story, confirming the beat is real and intentional. Detecting this precise correlation between a pulsar's light and its gravitational waves would be the ultimate smoking gun. Natural processes are messy and rarely coordinate their outputs across different fundamental forces with such perfect synchronization. A black hole merger screams in gravitational waves but is often dark in the sky. A supernova might blaze with light but produce a relatively faint gravitational rumble. Finding an object that sings the same complex mathematical song in both light and gravity would be a discovery of unparalleled significance. This is the power of multi-messenger astronomy. We are no longer just watching the sky, we are listening to it and feeling its vibrations. By combining data from light telescopes, gravitational wave observatories, and even neutrino detectors, we can build a three-dimensional picture of these enigmatic objects. A prime-numbered pulsar that whispers its sequence through the void in multiple cosmic languages is not just an anomaly, it is a signature, a deliberate design feature meant to be recognized by a civilization that has learned to read the universe with more than just its eyes. A new scientific truth does not triumph by convincing its opponents, but because its opponents eventually die. This stark observation captures the immense difficulty of shifting a scientific paradigm. The journey from a baffling anomaly to an accepted fact is a marathon of skepticism, a relentless process designed to break weak ideas and strengthen revolutionary ones. For the prime pulsar hypothesis, this path is only just beginning. The initial discovery would be met not with celebration in the halls of academia, but with profound and healthy skepticism. The first and most critical step is peer-reviewed publication, where the raw data and analysis are laid bare for the entire global scientific community to dissect. Every assumption is challenged, every statistical method questioned, and every potential source of error, from a computer glitch to atmospheric interference, is ruthlessly investigated. This is not a hostile process but a protective one. It is the community's immune system, attacking any claim that cannot defend itself with ironclad evidence. The history of astronomy is a graveyard of such anomalies, each one a lesson in humility. For decades, many astronomers were convinced they saw a network of straight lines on Mars, evidence of intelligent canals built by a dying civilization. They were wrong, misled by the limits of their telescopes and the power of suggestion. The case of N-rays in the early 20th century is another cautionary tale. A respected French physicist announced the discovery of a new form of radiation, and dozens of other scientists confirmed his findings. Yet the effect was ultimately shown to be an illusion, a product of subjective bias and measurement error. The prime pulsar signal must survive this same gauntlet. The next crucial phase is independent verification. A single telescope's data is not enough. Observatories across the world, and eventually in space, would need to point their dishes at the same coordinates, using different instruments and different software. to confirm the signal is real and that its prime number pattern is undeniable. They must rule out a local origin, perhaps a stray signal from a secret military satellite or an unregistered piece of technology on Earth. This collaborative, global effort is what transforms a curious finding into a solid data point. The slow, methodical ruling out of every conceivable natural explanation is the most painstaking part. Scientists will run countless supercomputer simulations, modeling neutron stars with every possible combination of glitches, magnetic resonances, and binary interactions. They will search for a natural law, no matter how complex, that can generate a clean prime sequence. Only when every known natural door has been closed does the extraordinary explanation of intelligence become the last one standing. This rigorous, often frustratingly slow process is not a weakness of science. It is its greatest strength. It ensures that when a claim finally emerges from the fire of scrutiny, it is no longer just a hypothesis. It is a new piece of reality, built on an unshakable foundation of evidence that has withstood every attempt to tear it down. We are likely in those early, electrifying stages, where a handful of researchers hold a secret that could change the world, and the long, slow work of convincing it has only just begun. Your personal computer could become a radio telescope. For over 2 decades, the SETI at Home project transformed millions of idle screensavers into a distributed supercomputer, sifting through the cosmic static for a sign of intelligence. This was not a passive donation, it was an active partnership. Everyday people from every corner of the globe lent their machines processing power, creating a collective ear far more powerful than any single observatory could build. That same spirit of public engagement has evolved. Today, online platforms invite citizen scientists to do more than just share computing cycles. You can now look at real data, classifying unusual signals, or even helping to design the algorithms that will search for patterns no one has thought to look for. This is not busy work. It is a fundamental recognition that the human brain, especially when multiplied by millions, possesses a unique pattern recognition engine. A professional astronomer might be trained to dismiss a certain type of anomaly as noise, but a curious individual with a fresh perspective might see it for what it truly is, the signature we have been waiting for. Democratizing this search does more than just accelerate the science. It fosters a profound sense of shared cosmic destiny. The question of whether we are alone is not owned by any institution or nation. It is a human question. By inviting everyone to participate in the search, we are collectively preparing for the answer. We are building a global community that is psychologically and intellectually invested in the outcome, ensuring that when a discovery is made, it is not a shock delivered from on high, but a realization we arrive at together. The greatest signal in history might not be found by a lone genius in a lab coat, but by a teacher in Lisbon or an artist in Seoul, someone who simply noticed a pattern that looked out of place. This mystery belongs to all of us, and every pair of eyes that scans the data brings us one step closer to reading the message in the stars. This relentless search for cosmic meaning is quietly seeding a revolution in our own technology. Every time we push our instruments to listen more closely to the stars, we are forced to invent new ways to see our own world. The extreme sensitivity required to detect a faint prime number sequence from 1,000 light-years away does not stay locked in an observatory. It flows directly into the satellites that form the backbone of our global communications networks, allowing for faster data transmission and more reliable connections. The sophisticated algorithms developed to sift through cosmic noise for a pattern are the very same tools that now power advanced medical imaging, helping doctors detect a tumor hidden in the complex data of an MRI scan with life-saving precision. Even the hyper-accurate atomic clocks needed to measure the millisecond pulses of a distant star are the bedrock of the global positioning system that guides our cars and smartphones. Each of these breakthroughs began not with a profit-driven business plan, but with a fundamental question about the nature of the universe. The economic argument for pure scientific exploration is often misunderstood. Funding a massive radio telescope can seem like an extravagant expense, a luxury when there are so many pressing problems here on Earth. But this perspective misses a crucial truth. The money spent is not vanishing into the void. It is a direct investment in the technological ecosystem that will define our future economy. It funds the engineers who design more efficient processors, the programmers who write more intelligent software, and the technicians who master new forms of precision manufacturing. These skills and technologies then diffuse into the marketplace, creating new industries and improving old ones. The drive to explore the cosmos is, in a very real sense, an investment in our own planetary future. It forces us to build a better toolkit, and that better toolkit is what we use to solve our greatest challenges, from climate modeling to sustainable energy. The ultimate answer to the prime pulsar mystery may be natural, but the journey to find that answer guarantees a more advanced and capable civilization right here at home. The moment a prime number sequence is confirmed as an artificial signal, the world will hold its breath. In that fragile silence, the responsibility of how to share this truth becomes as monumental as the discovery itself. Misinformation spreads faster than light in our connected age, and a revelation of this scale could easily be twisted into sensational headlines predicting invasion or apocalypse, triggering societal panic instead of profound reflection. This is where the quiet, meticulous work of science must meet the roaring engine of global media. Scientists, journalists, and educators will become the first translators of a cosmic language, tasked with a delicate balancing act. They must convey the staggering implications of the find while being brutally honest about its uncertainties. They will need to explain that we have found a signature, not a sentence, a message whose full content we may not understand for decades. Clear, accurate, and calm language will be the essential antidote to fear. Imagine the difference between a headline screaming, "Aliens contact Earth," and one that states, "Astronomers detect pattern consistent with engineered stellar object." The first incites a reaction, the second invites a conversation. This global teachable moment is a priceless opportunity to elevate scientific literacy for everyone. It is a chance to show how the scientific process actually works, with its slow accumulation of evidence, its peer review, and its willingness to say, "We do not know yet." Classrooms around the world could pivot to discuss the mathematics of prime numbers, the physics of neutron stars, and the philosophy of intelligence. The public would learn in real time what a technosignature is and why it is different from a spaceship in orbit. Preparing for this communication challenge is not a secondary task, it is a core part of the investigation. Developing protocols for transparent, coordinated, and responsible disclosure is as crucial as building the telescope that makes the find. How we choose to speak to each other about our place in the cosmos will define the legacy of this discovery for generations. The final proof will not be found in old data, but in the new eyes we build to see the sky. Our current telescopes have brought us to the edge of understanding, but to cross the threshold, we need instruments of a different magnitude. The upcoming Square Kilometer Array, or SCAR, is not merely an upgrade, it is a revolution in listening. Imagine turning a faint, distant whisper into a clear, distinct voice. By linking thousands of radio dishes across 2 continents, the SKA will create a collective ear so sensitive it could detect an airport radar on a planet orbiting a star tens of light years away. This colossal instrument will scan the prime-numbered pulsars with a resolution we can only dream of today. It will analyze the signal for subtle modulations, for hidden layers of data woven into the polarization or frequency of the pulses that our current technology simply misses. It could even discover dozens more of these mathematical beacons, mapping a network that our current, coarser maps have overlooked. The SKA transforms our search from eavesdropping on a single mysterious conversation to potentially hearing the full, sprawling dialogue of the galaxy. Yet for all its power, the SKA is still a remote sensor. It listens from a profound distance. The ultimate step in this investigation requires not just better ears, but a willingness to send out our own eyes. Projects like Breakthrough Starshot envision a future not of passive observation, but of active, physical exploration. The concept is as breathtaking as it is simple. Instead of a single, massive spacecraft, the plan is to launch a fleet of tiny, gram-weight probes, each equipped with a tiny camera and a communications laser. These nanocraft would be propelled not by chemical rockets, but by gigantic, ground-based lasers pushing on microscopic light sails. The acceleration would be gentle but relentless, gradually pushing these tiny messengers to a significant fraction of the speed of light. A journey that would take a conventional probe tens of thousands of years could be accomplished in just a few decades, while a prime-numbered pulsar is far beyond the reach of even this technology. The principle is what matters. It represents a fundamental shift in our relationship with the cosmos. We are no longer content to be cosmic homebodies staring out the window. We are learning to build a key and step outside the door. These are the first, tentative steps toward a future where humanity can move beyond speculation and into the realm of direct, physical observation, where we could one day fly a probe through the magnetosphere of an engineered star and see the truth for ourselves. These unsolved rhythms stand as one of science's most tantalizing frontiers, a perfect storm of astrophysics, mathematics, and existential wonder. Our journey has taken us from the cataclysmic birth of spinning neutron stars to the edge of speculation about civilizations that think in geologic time and build monuments from suns. We have weighed the terrifying risks and unimaginable rewards of answering a cosmic call, and we have considered the possibility that our galaxy is not a silent void, but a quiet, interconnected network humming with ancient data. The ultimate answer remains just beyond our grasp, a flickering signal in the vast dark. Yet the value of this mystery is not diminished by its uncertainty. The pursuit itself expands the boundaries of our knowledge, forcing us to invent new technologies, to question our deepest assumptions, and to see our own world with a new, fragile preciousness. Whether the final explanation reveals a bizarre new law of physics or the fingerprint of a cosmic companion, our place in the universe is forever redefined. We are no longer passive observers but active participants in a grand, unfolding story. So the next time you look up at the night sky, let your gaze linger on the darkness between the stars. See it not as an emptiness but as a canvas of infinite possibility. Question what you see and nurture that spark of curiosity. Every great discovery in human history began with a single, inexplicable observation, a puzzle that refused to be ignored. The greatest one of all may still be waiting, a sequence of prime numbers ticking patiently in the void, waiting for us to fully understand the question. We would love to hear your thoughts on this cosmic mystery in the comments below. If this journey has sparked your wonder, subscribe to continue exploring the universe's greatest secrets.